Hello everyone, this lesson is on astronomy. Astronomy is the study of stars and other celestial bodies, stars that we can see in the picture here. A bunch of other things we can't see, the so-called dark energy and dark matter. It's called dark because we can't actually see it. Indirect evidence, though, that there are other things that are out there having an influence on the movement of the universe and the movement of the stars and planets in the universe as well. And supposedly that dark energy and dark matter makes up about 95% of the universe. So what we're seeing in this picture here is a measly, 5% of what is out there. So you might be thinking, how does this fit in with anything else that we've done so far in the physics unit? We started off by talking about gravitational, electric, and magnetic fields, some calculations for gravitational and electric fields. Went on to electricity, motors, conductors, generators, transformers, electromagnetic radiation, reflection, refraction, diffraction. So how does that fit in with the study of astronomy? Well, when we do take a look at these stars, this is what we're taking a look at is actually electromagnetic radiation. So coming from our sun, which is a star, and other stars, they are generating electromagnetic radiation that covers the entire range, all the way from the very high energy gamma and cosmic rays, all through the visible light that we're seeing here, to the very low energy, longer wavelength radio waves and microwaves. So all of that, in fact, even though in the picture here we can only see the visible portion of the electromagnetic spectrum, they do in fact study all portions of it to determine things about the universe, like what are these stars made of? What is their composition? What is the age of the universe? What was happening in the universe in the past? What's happening now? And what will be happening in the future? And eventually, what's going to happen to these stars that we see in the picture here? So all of that is going to be related to this lesson. And again, the tie-in is with electromagnetic radiation. So the universe, they say, is, and again, the numbers sort of change as they come up with new information. But usually we talk around about 14 billion years old for the age of the universe. I think I have on the next slide a little bit more precise, like 13.8 billion years. So you've probably heard of the so-called Big Bang. And so that was what we refer to as the origins of the universe. Probably has nothing to do with any sort of explosion that we would typically consider to be a bang. But this is the term that we do use for it. So this here would now be our time zero in terms of the age of the universe. So where we're at today, yeah, this would now be the around 14 billion years. So we say about 14 billion years ago is when the Big Bang occurred. Again, this is sort of a rough ballpark figure that I have here. So early on, up until about this point here, 380,000 years after the Big Bang, very difficult to find that information, what was actually happening, because it may not exist anymore and it may not be accessible to us. But as we go to more recent time, going back only billions of years ago, then we can get some indication of how the universe has evolved or how it has changed over time. So this picture, certainly you don't need to know any of the details of this picture. So the dark ages that we kind of identify here, not really any physical bodies or large physical bodies. Then we do have, after about 300 million years after the Big Bang, first stars start to appear, early galaxies, the formation of solar systems, including ours, about 9 billion years ago, and then where we are today with the various different modern galaxies that we do have in these spiral galaxies that is showing in the picture here. But then, of course, the question also is, well, what about in the future? We kind of have an idea of what's happened in the past. What can we expect in the future as well? And we can also make these predictions by taking a look at electromagnetic radiation, which is coming from other parts of the universe. So this just kind of rehashes what I did talk about, much of the information anyway on the first slide. So yeah, big, well, some sort of explosion. Again, whatever that means is kind of vague. About 13.8 billion years ago. So kind of interesting. From what? So what was there 13.8 billion years ago? So sometimes they talk about matter being concentrated together in a state of infinite density. Again, what exactly that means is not entirely clear to me. Another one that's kind of interesting, unbelievably, is the idea that you can get something out of nothing. So from what is called a false vacuum, you can generate matter and antimatter, and it's from this, from nothing, that all of the matter that there is in the universe today may have arisen. So interesting ideas that are out there. How do we determine the actual age that it is? Somewhere around 13.8 billion years ago? Well, what they do take a look at is the portion of the electromagnetic spectrum, which is the microwave portion. Take a look at those cosmic rays. They're coming from the universe from very, very long ago. And the sort of afterglow that they talk about from the original blast does allow them to determine the approximate age of the universe. We're also going to talk about the fact that the universe, based on what we know right now, it is expanding. It was expanding at the beginning, in the middle, right now, and all indications is that it's going to continue to expand in the future, and not only expanding, but accelerating expansion. The expansion is getting faster and faster all the time. We'll take a look at something that is referred to as the red shift. This is really important that you know that term. That is the key indicator, taking a look at the red shift in the electromagnetic spectrum, that the universe is expanding and this expansion is accelerating. So what this also means is that the size of the universe from one side to the other is about 14 billion light years. This is the amount that light would travel in a year times the approximate age of the universe. So we study electromagnetic radiation coming from stars, and that does include our sun. This is our star, the closest star to us, the only one, of course, that we do have in our solar system. So what is going on? It's something that is referred to as thermo, which means heat, nuclear, involving the nucleus of atoms. Fusion means they're joining together. So what we'll see is there are very, very hot temperatures, and that involves atoms to join together, fuse together, and that releases a huge, huge amount of energy from the stars. And this energy that is released is in the form of heat and in the form of electromagnetic radiation, covering the entire range from very, very high energy gamma rays, again, to the very low energy radio waves. So yeah, fusion does just mean the joining together, and in this case, it is the elements. Enormous amounts of energy, and this is also why here on Earth, what we do look for is how can we actually use fusion energy to produce electrical energy? At this point, we haven't quite figured that out. We use nuclear fission that we'll talk about more in the next unit, but we haven't quite figured out how we could possibly use nuclear fusion at this point. So in order for this to occur, though, what we do need are really, really hot temperatures in excess of 1 million degrees Celsius. So in terms of our sun, I have a picture at the bottom here which shows our sun. Depending upon the distance from the core, there are different temperatures around the outside in what's called the corona. That is around the 1 million degrees. But I've seen ranges for the temperature of the sun going anywhere from 1 million to 6, or maybe even up to 15 million degrees Celsius. So it's at these temperatures where fusion does occur, and this fusion is what does lead to the creation of a whole bunch of the different elements that we find on the periodic table, created in the sun. This is going to be more of what we get into in the final unit of Science 30 as well. Albert Einstein's famous mass defect equation here, E equals mc squared. We're not going to talk about the details of that right now, but we will get into some calculations in the last unit. What it really says is that energy and matter, they are interconvertible, and possibly matter is just a frozen form of energy, and you can release that energy in the form of electromagnetic radiation. So what we will also see is this see here is the speed of light. It's a big, big number. And because it's so big, we can take just a minuscule mass and generate huge amounts of energy from it. And that's exactly what is taking place in our sun. So this is the reaction, the main reaction in our sun. It is the fusion of two different versions of hydrogen. This one here is deuterium, and this one here is tritium, fusing together to form helium and a neutron. But the key here, if we take a look at the picture, if you like it being a little bit more visual, is the energy is being released, and a lot of energy is being released. At the bottom, this is just a more simplified reaction, but it shows the same thing. Primary reaction in the sun, take hydrogen, convert it into helium, and that in turn releases enormous amounts of energy. I mentioned before, it's across the entire spectrum of electromagnetic radiation. The EMR, of course, goes in all directions, but one of those directions is toward Earth. And we've already seen what reflection is, bouncing off. In this case, it could be bouncing off of the atmosphere. That's what can happen. It can be absorbed by the atmosphere, warming up the atmosphere, or it can pass right through, having no impact on the atmosphere or the planet on any way whatsoever. Also important to understand that of the EMR that is directed toward the Earth, not all of it does reach the surface of the Earth. And this is really important. We do have an atmosphere that is essentially going to remove these ones at the bottom. So these ones here are very high energy, as we already know. And when they're high energy, what that also means is they can be damaging. So gamma rays, very high energy, extremely damaging to biological organisms, as are X-rays, and even high energy ultraviolet radiation. So our atmosphere pretty much removes all of the X-rays, the gamma rays, so it doesn't reach the Earth. Some of the ultraviolet radiation does reach the Earth, but remember that from the last unit, it is the ozone layer, O3, that is responsible for removing a large portion of the ultraviolet radiation as well. If we do want to take a look at these and study these, we actually can't use instrumentation on the surface of the Earth because it doesn't reach the surface of the Earth. What does reach the surface is this. So radio waves, infrared, which is heat, visible light. So this you do need to know that our atmosphere does filter out, remove some of the electromagnetic radiation, and it does never reach the surface of the Earth. A little bit of chemistry here, physics and chemistry. And we're going to talk about what's called emission and absorption, and the emission and absorption spectrum that we do see. So the pictures that I have here, you might recall that this is the Bohr model that we're taking a look at, where we have the inner nucleus, where we have the neutrons and the positively charged protons. Electrons are around the outside, in this case in the concentric rings. That is the Bohr model. And the Bohr model says that it's quantized, which means the electrons, they can only exist in this ring or in this ring or maybe in some other ones, but they can't really exist in between. So what the picture is showing is that initially the electrons are in the ground state. They're close to the positively charged nucleus. If you add energy, they can be bumped up to a higher energy level, which is now called the excited state. So various different ways that this can be accomplished, but one of the ways is by simply shining light or electromagnetic radiation on different elements. If it is of the right wavelength, and what we'll see is that every element is very, very specific in terms of the light that it interacts with. So this particular wavelength that we have here for this light, this particular frequency, what it shows is that this element is interacting with that light. That light is being absorbed by the electron. That light is now being removed, but energy cannot be destroyed. It has to go somewhere, and where it goes is bumping up those electrons into the excited state. So from here, we're not too interested in the picture at the lower right-hand side. What we're interested in is the other one, is that what can happen is this electron can fall back down to its ground state once again. And when it does that, it re-releases light or electromagnetic radiation. So what they have found is that every element on the periodic table has a very, very characteristic fingerprint for the wavelength and frequency of electromagnetic radiation that can be used to excite the electrons. Hydrogen would be different than nitrogen, would be different than oxygen in terms of the wavelength and frequency of EMR being absorbed and that's also being re-emitted that we see here. There's one other little aside. Whenever there's an energy transformation, some energy is lost. And that's why I've sort of drawn the wavelength here. And you'll see that when the light is re-emitted, it's actually a little bit longer. And that's because somewhere along the way, because this is an energy transformation, and they will not be 100% efficient, so some energy at least is going to be released in the form of heat or infrared electromagnetic radiation. Okay, so we'll kind of keep this in mind and probably have to jump back to this slide again. So the picture at the top here, it's showing what is called the continuous spectrum. So if we were to use an incandescent light, a typical old school light bulb, it does produce electromagnetic radiation of the entire visible spectrum. So all the way from the red through the green, the blue, the violet, all of those different colors. That's also the case with the sun or another star. So if we were to take a look at light that's coming from the sun, which is pure white light, and allow that light to pass through a prism. So this is a prism that we're taking a look at here. What it does is it splits up light, as we can see, into all the different colors. So incoming, we have the white light. Outcoming, we have this rainbow, and this is essentially what is taking place in the atmosphere, only what is serving as the prism are water droplets in the atmosphere. And that's why you see a rainbow. So a continuous spectrum, if we take a look at the right-hand side, it just means that, yes, we see all parts of every single one of the colors. There are no gaps, and that's why it's called continuous. All of it is visible. The one in the middle is called the absorption spectrum. So around any star, including our sun, there is going to be a gas. And that's what it's kind of representing with this cloud here. So that is a cloud of gas, which in reality would be all around the sun. Even though the sun is generating white light, before it reaches the Earth, it has to pass through a gas. And what's going to happen is that some wavelengths are going to be absorbed. And if they're absorbed, that actually means they're going to be removed. So now if we use that same prism, take a look at the light originating from the sun that has passed through a gas. Take a look at the spectrum on the right-hand side now. It's no longer the continuous spectrum. So these bands here that it's showing in dark color, those are the ones that are being removed. So this is called an absorption spectrum. It's also called a dark band spectrum because what we see are these dark bands. So that is the absorption of portions of the white light. So we don't see them as part of the continuous spectrum, and that generates our absorption or our dark band spectrum. At the bottom, equally important, is what's called the emission spectrum. So we can take any gas that we want in a lab setting. We can put it into a glass flask and we can excite the electrons. So going back to that previous slide here, so light can come in and excite the electrons, but we can do other things to excite the electrons. We can just provide electricity, and that could excite the electrons as well. So add some electricity. Spell that right on here. Add some electricity in the gas. It's going to excite electrons. And then what's going to happen with those electrons is eventually they're going to fall back down. So again, I need to go back to the previous slide to see that. So we've excited the electrons using electricity, but now they're going to fall back down and they're going to emit electromagnetic radiation. But if we have a specific gas that we're taking a look at, what we find is that each gas is very, very unique in terms of the pattern that we do see in the emission spectra. So that light is now passing once again through the prism. We can see here that it's showing all of the different colors, but when we look more closely, well, what we see is that actually the continuous spectrum is not there. What we see are these bright lines. That is the light that has been emitted by those electrons that were excited, and then they fall back down to their ground state. As they fall back down, they emit light. So for this particular gas, it shows that it emits purple, a couple bands of blue, a couple bands of green, yellow, and red. If we take a look at a different gas, it will be a different pattern. So kind of think of this as a barcode. This is our barcode standard, and we can have a standard for whatever gas we want to test. So we can test oxygen, and we can get the barcode, oxygen. We can test nitrogen, and we can get the barcode for nitrogen. We can test hydrogen, get the barcode for that. We can test helium, get the barcode for that. And every barcode is different for every different element. So how can we use this information together, the absorption spectrum and the emission spectrum, to learn a little bit more about the universe? Oh, and this one here was called a dark band spectrum. This one here is also called a bright band spectrum. We can now see these bright bands, and we have a whole bunch of gaps of things that we don't see. So in the classroom, we use a device that looks like this. It's about 15 centimeters long and maybe 10 centimeters high. What you do is you point this toward a light source, and then you look in here. Look into this end. So this here is called a spectroscope. And what it does is it takes that light that's coming in, it passes it through essentially a prism or a diffraction grating, and it creates a rainbow. So we can see in the picture at the left-hand side, this is the continuous spectrum. That's what we would see if we were taking a look at pure white light. Remember that all around the sun, though, there is a gas. And some of that gas is absorbing and removing some of those wavelengths. So when we take the spectroscope, point it toward the sun, what we do see, at least if it's a fair enough quality spectroscope, is we see almost all of the continuous spectrum, but wait a minute, there are some gaps. So this is the black band spectrum or the absorption spectrum when we take a look at the sun. So what does that mean? Something is removing these particular wavelengths of light. How can we actually figure out what is removing those wavelengths of light? Well, let's go back and take a look at a few spectra here. So the top one is the continuous spectrum. Again, really nice. We can see all of the different colors of the visible spectrum. The ones down below are the absorption spectrums for several different gases. So if we do take sodium, vaporize it, put it into a glass chamber, and pass white light through it, and then use a spectroscope to look at it, we see that there are some gaps. So what does that mean? Sodium removed all of those different colors. Electrons were excited in the sodium gas, and in the end, it ended up removing those particular frequencies and wavelengths of light. So notice here that if we do it with a different gas, mercury, it's a little bit different. So the last one here, last couple here, probably the most interesting, because what we have is the absorption spectrum. This one here is what I'm looking at. So this one is for this band. And the bottom one is the emission spectrum, and it's for the same element, lithium as well, that we're taking a look at here. So if we do take a look at a star, and if we see this particular pattern, we're missing some of the wavelengths and frequencies from the continuous spectrum. So how do we know what that gas is that's around that star? Well, from the lab, what we know is that if we excite lithium atoms, those electrons are excited and they fall back down. This is the fingerprint that we get. So this is the standard that we do have that tells us what is the fingerprint, what is the barcode for lithium. This is what it is. Now we take a look at this absorption spectrum. So again, let's pretend that this is using our spectroscope and we're taking a look at a star. We don't see all of the colors, but we see these dark bands. Now notice that the dark bands in the absorption spectrum actually match up perfectly with the bright bands from the emission spectrum. So this is how, if this were a star, that we can now take a look at that star and we can say, oh, well, that matches up with what we know from the lab, that it must be lithium that is surrounding that star, and that's what's removing those particular wavelengths of the electromagnetic spectrum. This picture just is to show that every gas, is a little bit different. So these here are the dark band spectrum that we're taking a look at. So again, this would be using white light, having it pass through these are the bright band spectrums. So this would be exciting the electrons in hydrogen or helium, neon, sodium, or mercury. But again, the key here is it is the barcode, and I'm just going to call it the barcode type pattern. That's unique for every single element. The combination of this with taking a look at the absorption spectrum from stars allows us to determine the composition of the stars. So that was a long-winded explanation for this. How do we know that our sun is made up of hydrogen and helium? Because we take a look at the absorption spectrum, we can compare it to the known bright band spectrum from the lab setting, and it matches up with helium, and it matches up with hydrogen. That's how we determine the composition of the stars. And so yes, the spectroscope, you should know what a spectroscope does. So it is the one that takes in the incoming light. There is a prism or diffraction gradient, and this is what it does. It splits the incoming light into its component colors. So I'm not going to go into all the details of exactly how it happens, but yeah, that's what it's trying to show again in this picture here. This is our prism right in the middle, and it's going to split it up into all of those different colors. Inside of the diffraction gradient, in fact, there are several mirrors that are going to be bouncing the light around, and then it passes through a diffraction gradient. But the outcome is that we do see the spectrum, and if there are any missing bands. So those missing bands would then generate the so-called dark band spectrum. So this one is taking a look at the absorption lines from our sun. So this is using a spectroscope on Earth, and what it shows is that before it reaches the Earth, these wavelengths or frequencies, so some of the red has been removed, some of the yellow removed, some of the green, blue, and purple has been removed. If we do take a look at the absorption lines from another galaxy, a star in another galaxy, so this one I think it's trying to say that it's 1 billion light years away, I want you to notice a couple of things. First of all, that the pattern is exactly the same. So this one has one in red, our sun. This one is in red, yellow, yellow, green, green, blue, and purple. Notice that in all cases, it's moved over a little bit. All of these lines have been shifted. And the direction that they've been shifted in this picture, it's to the right. And in this picture, that's red. So what we say is that all of these lines down here, they've been red shifted. So this would be an indication that this star that we're taking a look at actually has the same composition as our sun. But why are those bands shifted to the red? Why are they not in exactly the same location as where they are with our sun? And what we would see for the helium and the lithium when we test that in a lab and taking a look at the bright lines. So something else that we can tell about the universe is the fact that it is dynamic, it is changing. So a little bit of an analogy, if we think about a fire truck, a car, an ambulance that's moving toward us, we're standing still, after it passes by, you actually hear a different sound. It's a slightly different sound. It's a different pitch. It's a different frequency. So if you're standing here, and we do have a light source that's coming toward you, what happens is from that sound, the sound waves are actually compressed. So the waves are closer together. As it moves away from you, though, now they're stretched out. So what generates the different pitch or the different sound is the wavelength. So we've changed the wavelength. So this would be a high pitch sound, and this would be a low pitch sound as it's moving further away. This is what's referred to as the Doppler effect, and we see exactly the same thing when we take a look at light as what we see with sound waves. So it's also the Doppler effect, only now we're taking a look at light. So if I just quickly read through this, and then we'll take a look at a couple of pictures. If we do have a star that's moving toward us, so that's kind of like the picture up here, only now it's not sound, it's the light. Star that's moving toward us, the light waves, they're compressed. There's a shorter distance between the crests. If it's shorter, it moves it toward the blue end of the visible spectrum, and that's called a blue shift. If it's moving away from us, then the light is stretched out, and that is referred to as a red shift. So what this can give us an indication about is what are these other stars in the universe doing? Again, just a couple of pictures to hopefully make it a little bit more visual. So this is a star in another galaxy, another part of the universe. If it's moving away from us, the distance between the crests is longer. If it's moving toward us, the distance between the crests are shorter. So here on Earth, with our telescopes, looking out into outer space, this is a galaxy, a distant galaxy that we're taking a look at. And if it's moving toward us, yes, we would have what's called a blue shift. If it's moving away from us, what we see is a red shift. And this here is key for you to understand. It is the red shift that you need to know, because that is what we actually see. So this picture here, it does show, taking a look at a spectrum that we do have. This one doesn't have dark bands, it actually has the bright bands. It is an absorption spectrum. So this one here is, of course, continuous. Not only is it continuous or essentially continuous, but this is an indication that nothing is moving and that it's stationary. All of these lines are where they should be. If they're shifted over, in this case, towards the red end, this is what we call a red shift. If they're shifted in the opposite direction, this is what we call a blue shift, because we're talking about visible light. So again, what do we see? This is what we see. Stars in other galaxies, they indicate a red shift. What does that mean? It means our universe is expanding. So it's getting bigger and bigger all the time. And I mentioned right at the start, not only do we now know that it is expanding, but it's expanding at a faster and faster rate all the time. Finally, what about the temperature? Now we can figure out the composition of stars without actually going there. In fact, we can't. We can figure out what's happening to the universe. It's expanding by the redshift in electromagnetic radiation. We can also determine the temperature of stars. So we cannot send a probe to the sun, which is in excess of 1,000,000 degrees Celsius. We can't take a sampling of the gases, and we can't measure the temperature. So how do we actually know what the temperature of our sun and other stars are going to be? So they are massive, massive balls of hot gas. In fact, our sun makes up pretty darn close to 100% of the mass of our entire solar system. greater than, this should be 99, greater than 99% of the entire mass of all matter in our solar system comes from our sun. So absolutely massive. So it's the closest star. It is a star to us. Compared to other stars, though, some stars are bigger, some are smaller, some are hotter, some are cooler, some are brighter, some are dimmer. So ours is kind of, well, an average star by all accounts. And it's also referred to as a main sequence star. We'll see a graph of that shortly here as well. So the star color is related to its surface temperature. The star color is related to its surface temperature. So this is a pattern that you should recognize. Cooler stars are at the red end of the visible spectrum. As you go to the other colors, remember that red has the longest wavelength, and that's the lowest energy. As we go to the yellow and eventually the blue, these ones here have the shorter wavelengths. These are higher energy. Lower energy means lower temperature. Higher energy means higher temperature. So red stars will have the lowest energy. They have the lowest temperature. Our sun is yellow. It's somewhere in the middle. The hottest stars are blue in color. They do say that the overall average color of the universe as a whole is kind of a greenish turquoise. So kind of in the middle in terms of the temperature of the entire universe. This is just to, again, make it kind of visual. So down at the bottom here, this is measured in Kelvin, degrees Kelvin. But if we just sort of convert this into million, about 3.5 million degrees Celsius, those stars will be red. As we get hotter and hotter and hotter, they turn yellow, green, blue, and eventually even purple in the hottest of the stars. So bigger stars, it's going to be exactly the opposite with smaller stars. What do we know about bigger stars? Hopefully most of this makes sense. They're hotter, they're brighter, they have more fuel. However, because they have more fuel, they have a higher pressure, higher temperature, and that means they actually burn their fuel faster. So even though they have much more fuel, they burn it at such a fast rate that they actually have a shorter lifespan. They don't live, not that they really live, but they don't stick around nearly as long as smaller stars. Smaller stars actually stick around the longest. They have the longest lifetime. So I did say I would show you a graph here. So this does show the brightness of the stars, and it shows the color. So over at the far left-hand side, we have the ones that are blue. So those would be the hottest. As we go to the right, they get cooler and cooler and cooler. Where does our sun fit in terms of this picture here? Right in the middle. So this is our sun right here. So it also fits along this diagonal line, which is called the main sequence stars. This is where they follow the pattern that when they're bigger, they're hotter, they're blue, and they don't last as long. As we go down, they're smaller, they're cooler, and they actually live longer. So if we take a look at our sun here, it says the lifetime is 10 to the 10 years. That's 10 billion. So how old is our sun right now? About 4.5. So how much time does our star have left? Well, about 5.5 billion years remaining in the lifetime of our sun. If it were one of these stars over here, they have a longer lifetime. If we take a look at these ones here, this one has the lifetime of 10 to the 7 years, which is only 10 million. So we go from ours 10 billion to this bigger, hotter, more massive star, only 10 million years because it uses up its fuel much more rapidly. So there are some other ones that sort of fit outside of the categories, red giants over here and white dwarfs over here. They don't exactly follow that pattern that we can see on the main sequence stars. You do need to know a little bit about the fate of stars and star evolution, at least in terms of the basics, and that is what I do have on this slide here. So all stars, they begin as what's called a spinning and nebular cloud. Eventually, gravity is going to pull them in, and this increased pressure and temperature is what is going to cause those thermonuclear fusion reactions to take place. So for the main sequence stars, and especially if we're talking about our sun, this is what we think is that eventually, when it uses up more and more of its fuel, it's going to go through this cycle of expanding and contracting, expanding and contracting. Eventually, it'll reach what's referred to as a red giant, much, much larger in diameter, much, much cooler. Initially, they thought that this might completely engulf the Earth, that this is the Earth right here. And now they think that that's probably not going to be the case. It won't actually engulf the Earth. The Earth would remain outside of the radius of the red giant. Again, that would be billions of years in the future. What eventually does happen to a star about the size of ours? Well, eventually they form a very, very high density, small diameter star, which is referred to as a white dwarf. What about bigger stars? So still in the main sequence that we're talking about here. So this one here would be a yellow star. This one here, we'll call it a blue star. So what about these bigger ones? Well, they form now a larger radius super red giant. And in the end, or maybe not quite the end, but that might lead to a supernova, a huge explosion where we have this matter that's being scattered all around that particular galaxy. In terms of what's going on in stars, so for the most part, inside of our sun, it's generating helium. Bigger stars can form the other elements up to about iron, but what about all the other elements on the periodic table? Well, they think that it comes from something like the supernova, all of the higher elements. That's how they are formed, and that's where they come from in the universe. So all of these elements, they are formed either in the stars or when those stars explode in the form of a supernova. So if we do have a very high mass star, much, much higher mass than our sun, that can form an even denser star than the white dwarf, and it is called a neutron star. And the final possibility, if you have a super big star, there is so much fuel that when this supernova does take place, it forms a black hole. And so the story is with the black hole that it is so dense, gravity is so strong, curving the light, it's trying to escape outside of the black hole that it can't escape, and that's why it's not visible. Not even electromagnetic radiation can escape from the very, very dense black hole. And finally, this is in your data booklet that you just talked about what are called astronomical units. When we are talking about distances in the galaxy, in the solar system, they are huge, and so it often doesn't make a lot of sense to talk about in terms of kilometers. So instead, they use what are called astronomical units, or AU, and that's just the average distance between our sun and Earth.